sometimes if we don't know what the zeros are, we're going to have to find the potential zeros. These are called rational. Why are they rational? What's rational mean again? What's rational? Huh? No, you can be negative and be rational. Yeah. They could be all numbers, sure. But
it's a number that you know it's not repeating or anything.
Oh, yeah, okay, you're thinking rational, irrational, that's true. Yeah, that is true. I was talking rational in the sense of it's a quotient. So A over B, B over C. So rational zeros, we're just looking at quotients, which could be negatives, they could be integers, they could be a number that terminate, all of those were true. That's true. Okay, so it's called the rational root theorem, let's call it the RAT. And how do we find these potential zeros? It has to do with the factors of the very last term. And again, we put everything in descending order. So we have a zero, we have a constant probably in our polynomial, and that we're going to find the factors of that. And then we're going to look at the factors of the leading term. So the B and the C thing refer to, like, B is the integer factor of the constant. So B's are going to be the factors of that guy. And then C is the integer factors of my initial leading term. So I put it in descending order. I go find the very first coefficient. So that's this guy. And those are going to be the factors that I'm going to look at to find the C's. So B over C. I don't remember which is which. I just always remember that the B, well, this is kind of a dumb way of remembering, but B is before C in the alphabet, but when you're thinking B's and C's, you think opposite. You go to the last number to find the B's factors, and you go to the first number to find the C factors. I don't know if that works for you, but that's how I remember. B over C. You would think opposite of what you would probably intuitively do. All right. But then again. All right. So what are we going to do? We're going to go find them. We're going to find all the potential ones, and then that list that we generate would be what I test in synthetic division, and hopefully, I find a zero there. If I don't find a zero, I got to do something called approximations, and we'll just kind of talk about that later on. But we like it if we can find a zero. Those real zeros, odd degree polynomials, we've already mentioned in behavior based on the degree of the polynomial. So if we have a polynomial that's odd and it has real coefficients, then we're going to have at least one real solution. Think about any odd polynomial, the first to the third to the fifth. Those guys are always starting down, ending up, or reverse, right? Starting up, ending down. And that means they have to cross the x-axis at least once. And so that's what's happening here. At least one real solution means we have at least one x-intercept. Okay. So let's do this thing called the B's and C's. If you remember from Algebra 2, we call them the P's and the Q's. You remember that? P's and the Q's. All right. So they're the same thing. P's, Q's, B's, C's. So finding the zeros of this polynomial. Do I have to set up synthetic division for a quadratic polynomial? No. Can I? Can I set up synthetic division for it? Sure. You can set up synthetic division for a degree of 2 and above. So if we find the zeros, I'd like to see if that can factor. So looking for zeros, again, means this. That's right. Okay, so what do you think? Can I get the factors of negative 30 to produce a negative 13? Thank you. Is that possible? No, Miss Christina. Reason, looking for a job. It's hilarious. I mean, it's good that you're looking for a job. Oh. All right. Because I'm looking for a job. My daughter needs to work. All right, so can I factor this thing? Negative 15 and what? Okay, yeah, that's okay. But so remember, this might be a good candidate for the Xbox if you're an Xboxer. have in common? 3. What do we have in common? 2. So we have a 2x minus a 5 and a 3x plus a 1. And there I am. There I am factored. So this one has real zeros. And those zeros are going to be 5 halves and negative 1/3. All right, so that's just didn't have to do anything fancy with that guy. It has 2 zeros. And we said yesterday polynomials of n greater than 1 or greater than 0 have at least 1 0. And this one has 2 of them. All right, that wasn't all that exciting because we really didn't see the rational root theorem work. So this, though, is what we're going to be having to do. So you're going to be having to find both possible values and then plugging those values in to come up with our zeros. Yeah. What's up? That is a great pencil, yes. Mighty fine pencil. All right, so notice it's possible. That doesn't mean they are all going to work. These are possible rational zeros. So we have 2x cubed minus 9x squared plus 7x plus 6, and here is what we did. We looked at the factors. Again, remember that the constant is where I'm finding my b factors, and the lead is where I'm finding my c factors. So I look at factors of 6, and notice they're all plus minus. How come? Because a negative and a negative could produce positive, exactly. So I'm doing plus minus, plus minus, plus, so plus or minus 1, 2, 3, and 6. Those are the factors. Factors of 2, 1, and 2. Now we take them and we find out all of the possibilities. So what I do when I'm doing this is I'll take all of the b values and I'll divide each of those b's by each of the c's. So 1 over 1, 1, 1 over 1 half, 1 half. And then we'll do the same thing with the 2's. 2 over 1, 2 over 2. Well, 2 over 1, we don't repeat them. If I've already got them once, I don't show them again. So 2 over 1, we haven't seen that one yet. There it is. 2 over 2 is 1. Just don't need to repeat them. Then we do the same thing with the 3. 3 over 1. Oh, why am I pointing to 4? 3 over 1, 3 over 2. Again, 3 over 1 is new. There it is. 3 over 2, also new. And then lastly, 6. 6 over 1, 6 over 2. The only one that's new there is 6 over 1. So that's what I would do. Take all the b's, divide them by each of the c's, generate a list. For any repeated b over c values, we don't have to show them more than once. So there we go. There's all our possible factors now that we could test. So all of these guys now, we can plug into synthetic division with our polynomial 2, negative 9, 7, 6. And hopefully, we would find a 0. That would be nice to find a 0. And if we did, then we can break this thing down from a cubic into a quadratic. Any questions so far? Yes, Jane. You mean if there was a power of 12 to start with?
No, like then doing like plus minus 1.
Oh, okay. Okay, good. Good question. So I have 1, 2, 3, 4, 5, 6 times 2 possibilities. Each of those are plus or minus. So the question is, do I have to do this thing 12 times? And the answer is no. You do this. Well, I guess in theory you could do it 12 times because that means the first 11 that you tried didn't give you a 0. So you go until you hit a 0. And then we would restart this entire process all over for the new polynomial that we generate. Okay, so let's go play around with this. Let's see how it works. A little strategy here, finding rational zeros. So we have integer coefficients, degree of 2 or greater. And then we list all the possibles. So we find our b's, we find our c's, we find our b over c's. Remember, we need b over c's, not just b's and c's, but b over c's. Then synthetic division, write polynomial as our sum of our, or not our sum, our product of our linear factors, and then come up with our zeros. So the only thing new here, we've done all of this other stuff, except for these two. So really, these are the only two new steps. We've done that, written it as a linear. From that, we found our zeros. So the first two steps are now new because I haven't been given a zero, or I haven't been told this is a factor. Because remember, if you've been given a factor, that means you know a zero. If I know a zero, I've been given a factor. So let's try it out. Check it out. Am I going too fast? You guys all right? Okay, let's do. Who's going to be the B crew? Somebody give me some B values. What are the factors of B? Let's make sure we're talking about the right factor. Go ahead. Plus or minus 1.
Plus or minus 2.
I'm gonna be lazy and just show plus or minus in front. Plus or minus 2. 3. And 6, because B is again the constant term. Now again, make sure that you are in order with everything. Don't assume your polynomial is in order. Okay? C's, this is the hard one. I'm not sure you guys can handle this one. What is it? 1 and 2. 1 and 2. All right, that means the B and C's here are the same exact ones we just saw. And that's because this was the same problem, right? This was the same problem where I had B's over C's. This is what I'm looking for. Plus or minus 1, 1 half, 2, oops, why am I underlining? 2, 3 and 3 halves, and then 6. Again, all of those are plus minus. So there I am. These are the ones I'm now going to test. Test those numbers in polynomial p x equal 2x cubed minus 9x squared plus 7x plus 6. So we set it up. 2, negative 9, 7, 6. And then let's just do the shortcut method here. So do you guys want to pick one to start with, or just go in order? Just going to go with one. All right, we're going to go with, I know ones you're never going to use. You're going to do them at the very end because you hate them, and that would be fractions. But it might be a fraction. All right, so help me. Fill it in. What do I write? 2. Negative 7. 0. Oh, bummer. That one didn't work. Could I use that point, though? Is it, like, useless to me? That's useful to me. Because what is it? It's a point on my graph. All right. What are we going to test now? Negative 1. All right. So 2. Negative 11.
No, 18.
18.
And
It's not. Negative 18 and 6 makes it negative 12. All right. See, now here we keep going. Now what one are you going to test? Oh, whoa. Really? We're going 1 half. All right, we're doing it. All right, so what do I have?
You have
1 minus a 9. Right? This 1 minus a 9 is a negative 8. And then a negative 4 plus a 7 is a 3. And then a 3 halves plus a 6. Oh, man. 3 halves plus 12 halves, 15 halves. Okay, that one didn't work. We're going to go test negative 1 half now? All right, so negative 1 half. 2, negative 1 minus 9, negative 10. 5 and 7 is 12. Negative 1 half times 12 is negative 6, which gives me a 0. There we go. We have found our first 0 of negative 1 half. It is exciting, I know. It's like opening a present. So what do I do with that now? Well, what have we done in the past? Once we found this, what would we do? We go what? Mary Francis? Oh, well, we don't have to graph it. We use that thing. That was very descriptive. We use that thing. No, I don't know what you mean. Do you mean that we all, there we go. Do you mean that this is now a quadratic? Exactly, that's exactly what you meant. And then pull out a GCF. x minus 2, x minus, that is really nice. Thank you for factoring. Okay, now I don't know why I just did that. I wasn't looking for zeros. What I think I was supposed to be doing was looking for, what are we doing? Oh yeah, we are looking for the zeros. Okay, so what do we have? We have 3 of them because possibility, power of 3, possibly 3. In this case, we actually do have 3, and they're all real ones. So what are they? My zeros. Yeah, don't forget the one that you found in the polynomial division process. Sometimes we forget that guy. So we have negative 1/2, and then 2, and then 3. There they are. Hello. Okay, now, I could also take this and, let's say the problem didn't ask us for the zeros, but said, what are the factored form, or linear factor. Now I've got those as well. Right? So from the zeros, remember you can create factors. So our factors would be x plus 1/2, x minus 2, x minus 3, and then again that plus 1/2 we're going to write it. Yeah, we're going to write it as 2x plus 1. So I could have, even from doing the same thing, come up with the linear factors of that polynomial. Then now I can graph it, which is what Ray Francis explained, right? Take it, graph it. On my x-intercepts, I know it's odd, starts low, ends high. I can do my dance through the x-intercepts, and I have my graph. Questions on that? Yeah, yes, thank you very much. All right, hang on. Hold on to yourself now. Wait, I'll keep looking. Want to try that one, or you want to do this one? Okay, we're going yellow. We're going team yellow. Let's try that one. Right, so we started over, found our first 0. We get new B's, new C's. Should we test 1 again? It's a good idea because it might be a double root. It might be one that shows up twice, and you wouldn't see that if you test. Well, obviously you wouldn't see that if you tested it with the first polynomial because we already found that it is a 0. So let's see if it happens. 1 minus. Now remember, you're looking at these numbers now. You're looking at those guys. So 1 minus 5, negative 4. Negative 4 plus 9, 5. It works again. So we found another 0, and it's a double root this time. This is even more exciting than the last one.
It's opening a really big question.
This is like jumping out of an airplane with your parachute on versus jumping out of an airplane without your parachute on. That's a foolish thing to do. All right. But then we get x squared minus 4x plus 5 equals 0. And we get x plus 1, x minus 5 equals 0. Oh, you're right. I was not paying attention, obviously. All right. So then we're going to do our negative b plus or minus b squared minus 4 times ac. We get 4 plus or minus 2i over 2, factor out of 2 GCF. Those get to go away. And I find that 2 plus or minus I, those are my other zeros. Now, we were only looking for in this problem the roots. Now, when it says all roots, I mean I want the real ones and the imaginary ones. And so I have to include these. So we have one real root, which is a 1, and it's a double root, so I'm bouncing off of that. So my roots are x equal 1 and 2 plus or minus I. So from there, we can create our factors. X minus 1, because it's a double root, I'm going to square it. And then I'm going to have x minus 2 plus I and x minus 2 minus I. So if we get our polynomial in linear factored form, I'm going to have this. X minus 2 minus I, x minus 2 plus I. So there's my polynomial in factored form. Again, we were just doing this just for the heck of it. We weren't supposed to be doing all this stuff. All right, found our roots. Find our factored form. I could graph it from here as well. It is a, what degree is this one? It's a 4th degree function. So let's take a look at the graph real quick. It's a 4th degree function. Which means I have even. My lead coefficient, I believe was a 2. Nope, it was a 1. And it's positive. So that means my shape starts up and ends up for an even function that has a lead coefficient. And it's only going through x-intercept at 1, but it's bouncing off of that point. So here, at 1, we're going to bounce. No other x-intercepts. So what does it look like? It looks probably something like that. Parabola-ish looking thing, yeah, exactly. It's a little flatter again down there at the bottom. All right, so there's the beauty of the rational root theorem is I'm able to find all of these roots, factors, when I have not been given a 0. I just have to pick out my B's and C's and then test. Yes, David?
Get on the phone. We're just instead of writing it with parentheses for the 2 plus I, just write it with parentheses.
Like this?